Hello and welcome to our last unit in Regents Chemistry. This unit is called Oxidation and Reduction, but we usually refer to it as redox for short. First thing that we're going to need to be able to do in this unit is assign oxidation numbers, or oxidation states as they're also known. It's really important to understand that this part of this unit is something that you need to have a good handle on before going forward. If you can't properly assign oxidation states, the rest of this unit is going to be extremely difficult. Oxidation number or state is a charge on an atom or ion, or really any species that is in a compound or on its own in any chemical system. Oxidation numbers are found in the top right-hand corner of an element's block on the periodic table. So those are our oxidation states right there. Some elements, as we've noticed in the past, have one oxidation state, makes our life pretty simple. Some elements have more than one oxidation state. So in the case of something like nitrogen, what we've done up till now is we've just said, hey, we're just going to use that first charge most of the time. That works a lot of the time, but there are going to be situations where we have to use one of those other charges. So we're actually going to be figuring out how we figure that out in different situations. Usually, nitrogen is going to gain 3 electrons. Nitrogen wants to have a 8 electrons in its valence shell, so typically nitrogen will gain 3 electrons and therefore have a -3 charge. There are other bonding situations, depending on who nitrogen's hanging out around, where if electrons are actually being shared instead, the oxidation state of nitrogen might be a little bit different. So there are some rules for assigning oxidation states. Rule number 1. The oxidation number of a free element is always 0, and keep in mind diatomic elements are considered free elements. So, for example, iron has a charge of 0 when it's written as just typical iron solid. So that's just talking about a sample of solid iron. N2, nitrogen, has an oxidation number of 0 also. So there are actually 2 nitrogens in that compound, and each one of them has a charge of 0. And the N2 as a whole also carries a charge of 0. The proof for this is nitrogen has 26 protons and 26 electrons. We know that from looking at the periodic table. 26 positives and 26 negatives equal 0. It hasn't gained or lost anything. N2, each of the nitrogens has 7 protons. So we have a total of 14 protons. Each of the nitrogens has 7 electrons. Total of 14 electrons. Equal number of protons and electrons are going to give us neutrality. Number 2, remember the cation, or the positive ion, is most of the time written first. This is going to help a lot, especially with hydrogen. And very often, hydrogen has a +1 charge, like in acids, but not when it's bonded to a metal. So an example of this, let's scroll up, sorry. An example of this would be with H2O. In H2O, hydrogen's written first and has a charge of +1. Oxygen, as you know, has to have a -2 charge. So when we have 2 atoms bonded together like this, we expect them to have opposite charges. We have 2 hydrogens here, each with a +1 charge, balancing out that -2 from oxygen. So we have a +1 charge. In the case of sodium hydride, sodium has a very low electronegativity, so it actually loses its electrons to hydrogen. So this is a case where hydrogen has a charge of -1. Back to an example of an acid, and we remember acids dissociate to give us H pluses, so we do expect H to have a +1 charge in the case of HCl. Even though Cl has multiple charges, in this case we would expect it to have that -1 charge because it's written second, and also because it has a higher electronegativity, so it will steal electrons from the hydrogen. For our Regents chemistry world, oxygen is always going to have a charge of -2, unless it's in the form of O2, and it will have a charge of 0. There are times when this is not true in things like peroxides. We don't really deal with them in this particular unit. If you go on to college chemistry, that is something that you will have to deal with. But for now, now, for our purposes, oxygen will be either 0 if it's neutral O2, or it will be -2 if it's in a compound. In a neutral compound, the total charges must equal 0. In the beginning of the year, this is why we crisscross. So an example of NaCl, if we look up Na on the periodic table, its charge is +1. Cl's charge is -1. So +1 plus -1 equals 0. Neutral. In the case of magnesium, since magnesium has a +2 charge, but chlorine only has a -1 charge, magnesium's giving away 2 electrons for that positive charge. So it needs 2 chlorines to accept those, because each chlorine only takes 1. So our 2 chlorines times -1 gives us that -2 charge that balances out. For H2O, H has a positive charge, O has a -2 charge. So H in this case is written first. 2 times that +1 is +2, plus a -2 gives us that total charge of 0. Polyatomic ions are a group of atoms that are written with a charge together. So these will be given as having a specific total charge. So this oxidation state given right here is the oxidation state for that total ion. So if you look at table E, those given charges are representative of the total ion. Now what's kind of interesting here is we have a situation with nitrogen, which is nitrogen has a lot of oxidation states. So it's important to know this -1 charge over here to help us figure out nitrogen's oxidation state. In this particular compound, we have 2 oxygens, each with a -2 charge. So the charge of that individual oxygen is -2, and then we have 2 of them. So what this actually means is if we want to figure out the charge for nitrogen, we have 1 nitrogen, that's going to be X, and actually we can write this as -4. And this whole thing actually totals up to -1. So if I solve this equation, what I find out is that my charge for nitrogen is actually a +3 in this case. Oxygen is a lot less electronegative than, oxygen is more electronegative, so therefore it's taking electrons away from nitrogen in this case. Really, they're sharing them. Oxygen is just pulling on them a little bit more. We can do this again with this ion right here. So we have 4 times -2 represented by our oxygen. This -2 right here means our total charge. This whole thing has to add up to -2. We got 2 carbons in this case, so if I actually wanted to set up a equation for this, this would be 2x, because I don't know what each carbon's charge is, plus 4 times -2, which is really -8, equals -2. And if I solve this, I'll get +3 for carbon. So that whole thing adds up to that charge of -2. Last but not least, we have a phosphate ion down here, adds up to a total charge of -3. We have 4 oxygens, each with a charge of -2. So this is X minus 8 equals -3, which tells me my charge for phosphorus is +5. If an ion is written with an oxidation state, that's its oxidation state. So if you have a single atom ion like bromine, written as Br-1, its charge is -1. Ca plus 2 is written as +2. Very often these are actually written backwards, especially in this unit. Ca2 plus or Br1 minus means the exact same thing. You could put the plus sign before or after. Some words of advice from me. Number 1, find your sure things. This is an atom with only 1 oxidation state. Some of your really common sure things include oxygen, fluorine, they each only have 1 charge. Sodium, group 1 ions in general. Magnesium is another example, group 2 ions. Often zinc and aluminum are used. They each only have 1 charge as well. Identifying polyatomic ions can sometimes be helpful. These come from table E. What's interesting about polyatomic ions that you'll notice from this last slide is, from 2 slides ago, is nitrogen in this case has a positive oxidation state, which is weird. We're used to it being negative. Carbon right here, positive oxidation state. Phosphorus, positive oxidation state. So very often in the polyatomic ions, we have a nonmetal with a positive oxidation state. So sometimes that helps to identify those. Set up an algebraic equation to help you. And remember that everything in a compound has to add up to a charge of 0. Be very careful in accounting for your subscripts. And keep in mind that free elements, including diatomics, are automatically zero. So if something is written without a charge, meaning it's not an ion, it's just a neutral atom, especially if they put the little S symbol after it, that's usually a clue. You're looking for one capital letter there, that's telling you, hey, we got just one neutral atom right here. Or in a diatomic, it's still considered neutral, even though it's two atoms stuck together. So a typical problem like this, we have to assign some oxidation states for each of the species in this compound. I'm going to start with my sure thing, which is oxygen, and oxygen's charge is -2. So in my equation, or if I want to set up an equation to solve this and figure out what each species charge is, I know my charge for each oxygen is -2. I have 2 irons, so I'm going to do 2x. And then my charge coming from 3, I'm adding, to that, my charge coming from my oxygens. So 3 times -2. Sorry, I should use the dot. And the whole thing must add up to 0 because it's a compound. So this turns into 2x minus 6 equals 0. And then that's going to give me 2x equals positive 6, x equals plus 3. So that tells me that my charge for each individual iron is positive 3. So I'm going to rewrite this compound, or if you're given the compounds, you can just write the charges on them with a plus 3 right there and a -2 right there. So these numbers actually are representative of the charge of each individual atom, not the fact that we have 3 total oxygens. So when we're writing our oxidation states, we don't say oxygen has a charge of 6. There are 3 of them with -2 each. So if we find our sure things to the next example, sodium is a sure thing, has 1 charge. Oxygen is a sure thing, it only has 1 charge. So my sodium is my +1, and my oxygen is my -2. Sulfur is my mystery here. So I'm going to set up an equation to figure out what I'm missing. I have 2 sodiums. So 2 times +1 to represent each sodium, plus my sulfurs, which is going to be 2x, plus my oxygen, which is going to be 3 times -2. This is a compound, so the whole thing has to add up to 0. So that's for my sodium, my sulfur, and my oxygen. So this is going to give me 2 plus 2x minus 6 equals 0. 2x minus 4 equals 0. 2x equals positive 4. X equals plus 2. So what you can do if you don't want to rewrite the formula showing all those charges, we've already got our +1 for sodium up top, our -2 for oxygen. We just have to write our +2 for sulfur. Or you can rewrite it if you so choose. Next, we're going to tackle an ion. So this is a polyatomic ion from table E, and they're telling you that it has a -1 charge overall. Our sure thing here is oxygen. So to set up our equation for this, we have 1 chlorine. We're going to call that our X. We're going to add that to our 4 oxygens times -2. Because this is a polyatomic ion, they're telling us the whole thing adds up to -1, not 0. So this is X minus 8 equals -1. Very careful with your negatives here. What we're actually doing, remember, is adding 8 to each side. So this is actually going to become X equals positive 7. So in my ion, my chlorine has a charge of +7. My oxygen, 4, still has a charge of -2. And as a whole thing, it's carrying that -1 charge. It's a little awkward to write it this way. Really, we only do this as kind of part of larger problems. So here's a few examples for you to try. You can pause the video for a moment and try these guys out. So Your example for H2O is pretty straightforward. Remember, you're starting with oxygen being your sure thing. We're clued in that hydrogen is positive because it's coming first. So 2 times positive 1 plus negative 2 equals 0. The next two are very similar compounds, you just have different amounts of oxygen. So you'll notice the effect that that has on the charge of your nitrogen. I'm making hydrogen positive here because it's written first. So I knew this guy had to be +1. I'm calling nitrogen my x here. 3 times negative 2 is -6, and that whole thing equals 0. So this was what allowed me to solve for nitrogen being positive 5. In this case, +1 for hydrogen again because it's first, plus x for nitrogen, and I only have a 2 with my oxygen, so 2 times negative 2 is -4 equals 0. So that allows me to solve for my nitrogen being 3. Same kind of situation with sulfuric acid. This time we have 2 times positive 1, hydrogen's first, so it's probably positive, plus x for sulfur, minus, 4 times negative 2, or should say plus 4 times negative 2. That whole thing must add up to 0. This sodium is neutral sodium, so it has a charge of 0. Comparing that to the sodium ion over here, that's written with that plus or that +1. That's indicating that that sodium has a positive 1 charge and is operating as an ion there. Very often you'll actually see a little S like this next to a neutral compound to kind of help you identify that. Just telling you it's like a piece of solid, a piece of solid sodium. Also, sometimes you'll see a G, like as in this case, this diatomic chlorine. No charge written with it. Diatomics are considered neutral compounds. PO4 we actually looked at on one of our example slides. So X is for P minus, I'm going to add that to 4 times negative 2, which will become subtracting. The whole thing adds up to negative 3. Allows me to solve for 5 for my phosphorus. NO2, be careful. Sometimes people think, oh, that's a polyatomic ion, but it's not written with a charge. So this is actually nitrogen dioxide. So this is going to be X plus 2 times negative 2 for oxygen. Whole thing adds up to 0, positive 4 for your nitrogen. I gave you one with some parentheses to really kind of test your algebraic skills here. So I'm going to move this down here so we can really work this one out. Al2SO4 3. So this whole thing's going to add up to 0 because it's a neutral compound. Aluminum we know has to have a charge of +3. So this is going to be 2 times positive 3 from my aluminum term. Now, I have to distribute that 3 through that parentheses. You can also actually tackle the sulfate group individually. It's kind of totally up to you. So, since we don't know what sulfur's charge is, but this 3 is telling us that there are 3 of them, we're going to call that 3x. And then to talk about our oxygen term, we actually have 12 oxygens. So we're going to add this to 12 oxygens times that negative 2 charge, and the whole thing will add up to 0. So it's going to give us 6 plus 3x minus 24 equals 0. 3x minus 18 equals 0. 3x equals positive 18, therefore x equals positive 6. So kind of a lot of algebraic work there to get that sulfur as your positive 6. You could also tackle this because this is the sulfate ion. If you look this up on table E, you could separate this out from the aluminum. So X is still our charge for sulfur. We know that we have 4 oxygens times negative 2 each. That whole thing has to add up to negative 2. So this X minus 8 equals negative 2, or X equals plus 6. So 2 ways that you could get to the same place.